Hey guys, today's video is about writing cache-friendly code, and yeah, in this, what we'll do is I'll show you a couple of ways in which we can write. Just by changing the way we write the code, we can actually speed up the time taken by that piece of code. And the thing that we are using here is the underlying cache mechanism that our system provides. Yeah, with this, you'll get a better understanding of how exactly the data is actually laid on the RAM and how that data is getting read in the cache. So the entire underlying mechanism will be very much clear to you after this. Okay. Um, let me let me go to the code first. So yeah, the first part is this. As you can see, there are two functions here. We are just uh yeah iterating over a multi-dimensional array, two-dimensional actually. And the only difference here is the inner loop is I in this case, and the inner loop is j in this case. As you can see, j is the first index and I is the second index. So just with this small change, can we really speed up the execution time of the program? See. Okay, so with the column major one, we got 0.089 seconds. And yeah, with the row major one, we got 0.0255 seconds. This is like a 3 to 4x speed boost. Okay, so this is quite significant. Now let us understand what's going on. Okay. So this, just think of this as the RAM. My machine is 8 gigs, so that's 8 gigs of RAM. Now inside of the RAM, this is divided it into 128 byte chunks. So this is actually a number that is specific to Macs. For Linux machines, it is 64 bytes. You can check this as well this way. So as you can see, 128 bytes. Which is just saying that at a time when we are reading from RAM, we are pulling the data in chunks of 128 bytes and putting that into the cache. So let's say um, x00, my program goes to x00 and it wants to read that particular location. So what the operating system does is that let's say x00 is over here. Now this x00 will be read, but the entire 128 byte chunk around it, that will be read and put into cache, right? So once we have this 128 bytes into cache, so let's say, yeah, so something, so the x00 is basically, let's say, 32-bit integer, which is 4 bytes, right? Which means in 128 bytes, uh, 32 of those integers will be uh, pushed into the cache. And reading from cache is very, very much faster than reading from the RAM, right? So how so over here, what's going on is x00, x01, x02. In this way, the multidimensional array is actually laid on top of the RAM. This is how the data is laid out. So what happens is when we read x00, 01, 02, and 32 such integers directly get read into the cache. And now when the loop goes to x01, it just has to read from the cache. From 02, it just has to read from the cache. The RAM, it going to the RAM is not required anymore. That is where the speed, we are actually getting the speed bump. Uh, yeah, so that's the core reason. Now that you know how at an underlying level uh, the program actually stores memory and stores integers. What do you think will happen in this case? So what's going on here is that we are just copying we are not actually computing this particular not doing all of these computations. The reason being that there were a lot of these include quite a lot of computations and the memory access as well. And actually, yeah, we just looking at the time difference was not possible in this case. The memory access was not the bottleneck, so that's why I created a different code. Over here, the only difference is that this is a 16-bit integer array, and this one is a 32 bits integer array. So what do you think? Which one will be faster? Just thinking about from the concept that I have just taught you. If you had the time to think about it, yeah, let's just try to run it, and I'll tell you the answer then. 3, 4. Okay. So as you can see, there is a direct, a very close to 2x speed bump, right? And so yeah, just think about it. What could be the reason here? We are using 16-bit and 32-bit integers. The reason is if we go back to the uh, in this 128 byte chunk, how many of uh, 32, we were taking 32 and 16, right? Yeah. So 32 bits means 4 byte and 16 is 2 bytes, right? So double the number of 2 byte integers can be stored in this 128 byte chunk, which means completely traversing the array will require much lesser RAM access, right? Because in one RAM access, we are bringing 128 byte worth of data into the cache. 128 byte worth of data, which means uh, 64 of 2 byte integers, but 32 of 4 byte integers. So exactly the double the number of RAM access would be required in case of 32 bit integers. And that is the reason why uh, the 16-bit function is exactly double in speed. Um, yeah, I think that's all for this video. Let me know if you have any comments or questions.